Okay, good morning everyone. Welcome to the new video series related to simulation softwares. So, in this video series, I'm not going to solve any MCQs or problems or any structured solutions and so on. And this time I'm just going to look into new, what you call simulated experiments. What are the different softwares which are available for simulation? And what I thought was something different like this. I'll take up one concept and then I look up like how can that concept be explained in different methods and that too making use of different simulated softwares. So this is all about it. So towards it, I am now beginning with the first concept for today, which is on free fall. Okay, let me know your feedback as how it is useful. I think most probably it will be useful for mostly for teachers or facilitators rather than the students. Of course, students will also find it interesting, but for facilitators, it will be very much useful, I feel. The links that I'm going to use in this video series, the softwares or whatever web pages that I'm going to use will be there in the comment section below. So you can look into it and you can also utilize it. Maybe if you get much more information than what I'm teaching over here, what I'm lecturing over here. So you can also let me know through my dedicated WhatsApp group. I'll also put across that WhatsApp group over there. So any discussions here of related to IB, we'll just discuss about it. And of the late, we came to know that our recent IB exams got over, and there were sayings that people, students reported to me saying that some students said that the first paper was a bit difficult and second paper was easy or first paper was easy. So there are mixed reactions. Of course, there was one one question in SL which was related to EMF systems. And in fact, EMF is not being taught, and the flux and the EMI was not being taught. So, okay, let us see like what IB decides about that question. Okay, now without wasting your time, let me proceed with this. Just a moment. Okay, let me share my screen. I'm not going to do anything directly on what you call just a moment, on writing and presentation and so on. I'm just going to use only the websites that I have looked into. All right, let me share this. Right. So shown here, so okay, we all know what we mean by a free fall. Free fall is nothing but you take an object, drop it from a certain height, and as a result of it, when it comes down, we estimate what is the distance taken, and we find out what is the time taken for the given distance to be moved. Okay, and this free fall happens because of gravity, and in Earth, it is seen to be g equal to 9.8 meter per second square, and in other planets, it might differ. Okay, that's what we know, and generally, it's a very small concept. That's what even I had been thinking of. But later on, when I started to look into it into detail, I thought, why not we extend it to a little bit until gravitation? Okay, and there are many questions which have been asked in IB papers related to free fall. They may not be directly related to free fall, but something like kinetic energy versus distance, kinetic energy versus time graphs can be asked, or maybe distance versus time graph can be asked, velocity VT graph, time graphs can be asked. Okay, and related to gravitation also one can coin a question. There are several questions one can coin using this. And this free fall is very much instrumental, very much important in answering those two. And if you understand this concept properly, then I think you'll be able to answer any questions appropriately. Okay, now let us begin with this. This is one of the basic tools that I looked into. Of course, there are many tools available. Of course, most of the time we'll be using only PHET. But what I would like to show is, apart from PHET, there are several other tools. So let us look into it. The first tool is by NC State University. The URL or the link for it will be shown below in the comments. You can look into it. So here what we have is we have a ball over here, and we can actually, so there are controls given over here. There are controls here. You can select the gravity value. For the gravity is shown, initial height is shown, and you can change the height, and thereby you can drop it, and you can estimate, or you can find out what is the VT graph and distance time graph gives you. Okay. Now what you can do is you can initially, let us say for example, reset over here. So the ball is taken at a height of 125 meters, and from here if I drop it, and we are going to conduct this experiment in Mars. When we do this, the acceleration due to gravity is 3.71 meter per second square. When I drop it here, so you see the ball moves very slowly because the attractive force due to the planet is much lower, and you see the VT graph shows a straight line, while the distance time graph will show you something like this. Distance or displacement time graph will show a nonlinear curve. Now if I change this to Earth, then I'll reset this and go back to this, then you see the speed of this ball is much more enhanced, and you see the earlier the slope here was this much, and now you see slope is much higher over here, right? In a similar way, if I go to Jupiter, for example, and repeat the same experiment, let me reset this. Jupiter, the gravity is more than twice, 2.5 times that of the Earth. When I do this, then you see it approaches the ground much more faster, and the graph looks like this. Okay, what kind of questions we can ask? We can ask the question. So if the graph is like this, or if the slope is much more steeper or lesser, then what do you infer about the gravity? We can ask about that using this VT graph. And also, if VT graph is given, then how does the distance time graph change? You can ask this question also. Okay, so this is what we can understand, or we can do one part of the learning what we can get from your free fall. Okay, now let me take up one more simulation apart from this. Now this simulation is done by the physicsZone.com, and here what you see is that the y-axis has timings, and as for every 0.1 seconds, image of this ball is being taken, and as a result of it, they are finding out what will be the distances covered. Now let me reset this. You see there's a tray here, there's a ball over here, and for every 0.1 second you are taking a camera with you, you're taking click the pictures on it, and you're going to find out where is the ball at every 0.1 second. When I play on this, you see this is what you get over here: 0.11, 0.186, 0.301, 0.374. Randomly it has been chosen, and you see the distances which are being covered by the particle over here. So this is what happens over here. So this tells you about so that in a free fall experiment, even though when you take the consecutive time interval, the distances traveled by the particle is not uniform. So it's not an uniform velocity motion, it's an uniform accelerated motion. And this also tells you that whenever you have a uniformly accelerated motion in consecutive time intervals, the distances traveled by the particle will be larger. It will not be smaller. For example, if you look at this distance here, this is around 0.11 minus 0.186. If you take this difference and you take, let us say this difference, almost they are one and the same. Okay, but still you see the difference between these two, the heights here and the distance here is much more different. Okay, so that we can infer from here. Okay, now let us move on to one more simulation. Same simulations. Okay, now this is a free fall once again. So here what we do is there's no ball or anything over here, but you can click the cursor. Okay, so I'm going to click somewhere over here. Let's say I keep it at 10 centimeter. I click here, then I observe that the passing speed is 1.4 meter per second, which means how did it calculate? It calculated between these two spots. Between this spot and this spot, what is the distance taken by the ball to cross this divided by time taken? Okay, since the distance is very small, so you can say almost it's an instantaneous and average velocities will be nearly equal. And we have found out the velocities when you drop it from a height of 0.1, which was into a 1.4. If I increase the height, then you see it becomes 1.97. If I still increase the height, this becomes 2.43. If I still go to 40 centimeters, it becomes 2.8 meter per second. Okay, I still go higher, 2.9391, right? So therefore, as the distance increases, the speed at which it crosses this particular path also increases. This is what we can say over here. Okay, now, so which means we can plot a graph of velocity or speed versus the height. You can ask the students to actually take a notepad and then calculate, or for a different values of this one, you can choose the height as an independent variable, and you can use velocity as a dependent variable, and you can ask them to plot a graph of these and then ask them to infer based on this. Okay, what do they understand? What is the math behind it? Okay, this could be an excellent intro to your the internal assessment. Okay, what is your independent variable? What's your dependent variable? You can put it across. Of course, you cannot have any control variable here. Your control variable is only the ball. Okay, but still the surface and nothing is seen over here clearly. So therefore, it's just a small dot. So you will not be able to quantify that. But still, to understand the independent and dependent variable, this could be a good approach. Let us move on to the next one. Once again, a free fall. Just give me a moment. Right. Now in this simulation, I already opened all the simulations. Okay. So initially when you start with the simulation, I just refresh this because I adjusted something over here. When you start working on this, you might not get the same kind of simulation. Now here, now this is the way how by default it looks like. Now as a result of it, okay. So what I do is this height is much lower. I am not happy with this. I would like to increase the height. So there's a h equal to 5 meters has been given over here. I will increase this height. I'll show you what's the consequence of this. When I increase it, what do you see? There's something like two walls over here in which the person is in the elevator, right? So I will increase this height. When I increase it, I made it to something like around h equal to 5, h equal to 25. I think this glass walls that I have put over here is increased to maximum over here. And then what I do is, there's a graph over here. So usually what we do is we conduct an experiment and then we find the graph. Now this one has a different story. You change the experimental values by altering the graphical values. Okay. So, different ways of doing things, okay, will help a learner to learn effectively. Okay. That's why Howard Gardner says that there are 8 different ways of learning. Okay. You take up one concept, okay, only with one concept, you will not be able to learn effectively. You need to have different methods of learning. So this is what we are doing. Okay, so just a talk and talk will not be useful. So you also need to do it something else. So towards it, what I do is there's a drag here. I'll click on this and pull this one here. What is it I have done? I have pulled the elevator from here to here, right? And then what I do is I still increase this one here. This at a time of 0.1 second. And then I put this one here to some extent over here. When I do it like this, what does it tell you? That means the particle or the elevator, the moment you start the simulation, is going to go up by a certain height. See, it's not going to be 25. Now maybe it is going to 26, 27 at this point. And after that is going to come down because of gravity. It's going to come down. And then once again, it comes over here. Okay, maybe this is a water surface or a sand surface. The moment it comes here, it bumps or it bounces. And then again, it just oscillates over, right? So as a result of it, what happens to the graph is also been shown. Okay, this could be understood. Now, if I run this, okay, I will not be able to see any difference over here. Let me run this if you want. I'll just run this. And you see, there's a line, there's a dot which keeps on moving like this along the path as it oscillates. This is what you can see. But what you can understand is, you can give this graph to a student and ask him to write a story based on this, right? Usually, we depict a story and then we ask them to find out what is the graphical notation. But here, we are doing the reverse part. We are giving them the graph and we are asking them to write a story on it, which means now he can write something like initially the person is at a height of 25 meters and then he goes to a certain height. The elevator goes to a certain height of 26 or 27, and after that it drops. Okay, it keeps on coming down with the same acceleration due to gravity, and hence you will be able to find out, okay, what is the how does the height varies with time. You'll be able to find out the velocity. You'll be able to find out what happens to the height over here. When does the velocity become zero? You can say about all these things. One more important point here is that you look at this g force over here. What is g force? It tells you about the apparent weight. Okay, when this person was at a certain height, stationary, then maybe it says it is equal to 1g, which means what? The mass of this person is 1 kg multiplied by g. This is what this was his weight. But as the elevator goes upwards, comes downwards, and so on, you see the apparent weight keeps on changing. It keeps on reducing, and finally it becomes zero over here, and sometimes it becomes negative, and once again it increases, goes to a maximum, then again reduces. You can ask the student about why does these kinds of things happens. Okay, we all know what is the answer for this. Okay, how do you calculate the apparent weight? It is not just mg, it is something else. It's mg minus ma or mg plus ma, depending upon how the weight is now moving across. You can get an answer from there. So what does it help you? Using the single concept of free fall, you are also able to describe the free body diagrams, right? So this is how it is useful. Then you can look at this over here. So it increases, it decreases. What happens to the vertical velocity? How does the vertical velocity changes? So that means now you're focusing more on the VT graphs, right? And now let me move on to the next one. There's one more simulation. See how many simulations we have. Now this example, this simulation, this is from Desmos. So as you see, so I have particularly opened the kinetic and potential energy. So how do you get the simulation here? So you can click here. There are several what you call play buttons being kept over here. Time, it's automatically been simulated, and the initial height is 10 meters, and the mass of this is 6.04. You can actually reduce the mass and ask the question, the same question. Okay, and then G equal to 3. I will not use Earth. Okay, I use some other planet at G equal to 3. Maybe if you want to keep it at Earth, you can drag it down. You can keep it to now G equal to 12, 11, array. So fast. Okay, G equal to 10. This is what I do. Now let me start with G equal to 10. Okay, how do you get this kinetic and potential energy? So it's here. See here you see kinetic and potential energy. Initially this will not be clicked. So therefore now it has been activated. So kinetic and potential energy of this has been given. Now when you look at this here, the ball is bouncing here to the ground and moving upwards. When the ball comes to the ground, what is the velocity of this? The maximum velocity of this, maximum kinetic energy of this? Maximum kinetic energy goes to around 584 joules over here. When it goes upwards, the maximum height, what is the maximum potential energy? That's also around 601 joules. 601 joules. Here also do I get 601? This also, let me just check it out. Yes, you get around 604 there. 600 and yeah, 604 over here, because it's going so fast, I was not able to detect it. So definitely it goes until that. So thus you will be able to say the kinetic energy at this point is equal to the potential energy at that point. What does it tell you? It tells you about the conservation of energy, right? Just a minute. Okay. So thus you see, you are able to explain the conservation of energy using free fall. Okay. And then you can also ask the student, maybe you can actually reduce this. Now you can ask the question, if suppose if the value of G is reduced, then what will happen to these energies? Will the kinetic energy and potential energy remain the same, or will it be different? Okay, so you can ask this question. Maybe I can now reduce it to much lesser. Maybe I'll put it here to G equal to 6, G equal to 3 or 2 or 1. I'll put it this where I use by default 3. Right, I'll put in G equal to 2. Now look at this kinetic energy here. The kinetic energy at this point, there it was 0 at the top, it was 0. At the bottom, it's around 117 or something. So now you see the kinetic energy and potential energy changes when the value of G changes. You can explain this, what is this happening? Or you can ask the student, okay, show by necessary equations, why does this change? We are just using only one concept, and we are changing a lot of things over here, right? We can do all these things over here. Then where are we now? We are here. Now let us look at one more. See how many simulations based on this. Now this is really good. So what does it tell you? It tells you, let us say about the free fall calculators. Okay, so you have chosen different planets over here. For example, if I choose a planet of Earth over here, the value of G is 9.8. And if I choose something like height is equal to 1000 meters, which means what? I take an object, go to a height of 1 kilometer, and from there I drop it. And I ask the question, how much time will it take for it to drop down to the Earth? Usually, it doesn't take 14.28 seconds. It takes much more than, larger than that. Why? The reason is because there is a air resistance. But in an ideal condition, in a vacuum, this is what can happen. And the velocity in a vacuum will be around 504 kilometers per hour. Okay. Usually what happens is this where what was interesting to me. Okay. When I asked this question to one of my students, he said, could be around 100 meters per second. I just told him, can it be 100 meters per second? Can it be 200 meters per second? Then I said, sir, maybe it is 1000 meters per second. Then I told him, if this was 100 meters per second, first find out. Let us say, for example, if it is 140 meters per second, the kilometer per hour, in kilometer per hour, this is 504 kilometer per hour. Okay, so therefore, so when an object falls onto it, you should know the relative values of it. You cannot just keep on saying, okay, this could be 100 kilometer per hour, 100 meter per second, 200 meter per second. Though numbers seems to be fancy, but you should know when you convert it into kilometer per hour, how large a quantity can be, how small a quantity can be. I've seen some question papers which tells you something like the charge, sorry, not question papers, some answer papers which students write. If I ask them, what could be the charge on a capacitor? They say maybe around 200 coulombs. Hey, what is this here? Can a capacitor store 200 coulombs? Is it possible? Okay, 1 coulomb charge itself is very, very high. So how much high is high and how much low is something which one should understand, right? And you can actually change the planets. For example, if the same substance is being dropped from the sun, it takes only 2.7 seconds, which relatively tells us what is the effect of gravity, how much fast it is going to attract or grab an object, right? Okay, let me go to the next one. What is the next one here? Okay, so this is a Russian website which I initially found to be bit difficult to understand, but anyway, I took the help of ChatGPT, put out all these labels and try to understand. But anyway, so this gives you this very much similar to the repeating part of it. But okay, this is interesting. So for example, if I click on this particular planet, on Mercury, okay, so what happens to the vertical distance traveled by it, and what is the velocity of the particle with respect to time? VT graph and V of t is being shown over here. But now the question here is that why are we getting this negative values? So this you should be able to ask them. Okay, why are we getting something like a graph should always start from here, but why is it showing something like this? What's happening over here, right? So this again related to the kinematics part. So you can look into it. You can click on this. You can see how does the particle moves over here. So see, because when you just look at the graph, you may not be able to understand. But if you play this over here, reset this first. Let me reset this. Okay, and when you play this, why do you get the negative graph? You can see from here, it is dropped from a height of -1. What do you mean by -1? What do you mean by 0 here? Okay, how do you define the origins? Okay, so usually our students always have this difficulty. We always assume that the origin is with respect to the earth. But if the origin is chosen at a different point, then how will the graphs look like? Okay, so all this critical thinking you can easily understand by making use of these kinds of websites. Okay, we can directly tell them, but okay, as they start using it, they will come to know, okay, how does things vary over here. Now, let me go to the next one. Okay, now what is this about? This is about something like a gamified approach of gravitation. Now we started with kinematics, we went to energy, we went to several places. Now what we are looking at is okay, something like gravitation. In gravitation also there is a free fall. Now where is the free fall? For example, this is the sun over here, this is a planet over here. When the planet is nearby to the sun, okay, what happens is there's only gravitational potential acts on it, and as a result of it, it will get attracted. Okay, and it is under the free fall of it. So therefore, there is also a free fall over here, and thus you see the planet starts orbiting only because under its own free fall. Now we can say, when I ask a student about, okay, so is the moon undergoing a free fall? They'll definitely say, no, it's not undergoing a free fall. It's just moving around a circle. But actually speaking, moon is undergoing a free fall. Okay, and now, so you can understand from here, what you can do is you can actually put a satellite here. Let me try to put a satellite here and show you how does this work. I'll do one thing. I'll take a satellite here. There's a satellite here. I'll click this. Maybe I will keep it somewhere at farther distance. Oh, it's the arrow is that side. Maybe I'll keep it nearby here. I'll keep it here. I kept it there. Now you see the satellite moves slowly over here. It's moving approaching towards the sun, and it has moved over here. Now, as it moves away, does it move completely farther away? It doesn't move completely farther away because there is one more planet over here. Okay, and the influence of this also being felt. So it once again starts coming. Recently, I don't know whether you have seen this particular thing has been playing a lot of role in Instagrams. Okay, so I have seen something like there was a meteor which was about to strike the Earth, and suddenly then UFO came in between, and as a result of it, it got deviated. We really do not know how much is this true or false. Okay, but okay, one can actually try doing this. Wow, see, look at this here. The path of it is completely changed. A very similar thing that happens. If this was the Earth and there was one UFO, this blue color one, if I assume this is a UFO, and if it was coming like this, and that was the meteor, the white color one, okay, it came over there and then it just escaped and went away like this over here. If you have seen this previously, if you had, you can run this video backwards and see, okay, the same thing can be observed. Right, you can add any number of objects for that matter. For example, I can take up this cluster of several objects over here, okay, rocks for example. I can put it over here and see what's happening over here. See, so nicely, okay, how there's a collision taking place or there's a rearrangements of the objects takes place. You can do many things using like this over here. Okay, so you can give this gamified approach to students, ask them to work on this, okay, to see, while we start teaching, if it is just mundane teaching over there, so it's always boring. So instead of it, if we give some things like this and ask them to do some wonderful patterns, how fields actually play a role into it. Okay, so students will always be happy to work on this. So physics learning, I feel always it should be something like, okay, fun. It should not just be writing on a board and doing things like this. Okay, now let me move on to the next one. This one is tells you. Okay, let me just refresh this and show you. This is really an interesting thing that, okay, one can do with this. So what does it tell you? Okay, let me just minimize this. Okay, so here this is once again under free fall, but we are going to drop several objects based on this. Okay, so what are the objects that I'm going to drop? Now, the first object that I'm going to drop is, say for example, I'm going to drop sand over here. I take up this, a very simple simulation. I drop the sand. So what happens is when it falls onto it, the heap actually takes up something like a triangular one, right? Now let us say for example, instead of sand, if I take wet sand and I drop over here, now you see it forms something like a barrel because there is a cohesive force in between them. Now you can explore something like what instead of gravity, apart from gravity, if there is one more force acting, now we are doing a different one. In free fall, what else can happen? What is the behavior or nature of a collection of objects under free fall? We can ask this also. Now let us say, for example, if I take something else, let us say I take powders. I take powders and I take ash, for example. Now how does this behave? Now you see it falls a small heap over here. Okay, so with this heap and this one is very similar to it. There's not much of difference. Okay, if I take gases, okay, and then let us say I take oxygen. I take a lump of oxygen and drop here. Now, is it getting affected by gravity? It's not really getting affected by gravity. It is just getting dispersed over here. Now, what will happen instead of oxygen? If I take some other, say, let us say, for example, if I take propane, okay, and drop over here. No, propane is also moving further away. Okay, or maybe, okay, let me just clear this. How do I clear this? There should be some way to clear this. Erase. Oh, I don't want to erase this. Reset. Okay, I'll reset this. Let me take up something. Let me take, for example, bubbles. Bubbles, carbon dioxide. Carbon dioxide is a dumb gas, right? Okay, let me take up this carbon dioxide. Oh no, carbon dioxide also gets dispersed. Then what else can I use? Fragrance. Now, what happens in fragrance? The dispersion of fragrance is also seen to be much, much higher. Okay, it also starts moving away. Okay, if I take liquids, let me once again. Where did I lose this? I lost it somewhere. I'm looking for reset. Yeah. Okay, let me take up something like some liquids. Liquids. If I take liquids and I take, let us say, soap or maybe oil. I take up oil and drop here. So oil will form a layer almost. Okay, let us say, for example, if I take something which is, I don't want water, juice, milk, vinegar, mercury. What will happen to mercury? Mercury will also spread out. Okay, and what else can I take? Blood, poison. I don't want to take poison at all. Let me take a viscous fluid, honey. Okay, let me take up honey. Honey forms a heap-like thing initially, and after some time it settles down. Okay, so like this, at least I can understand that every object will not behave very similarly when it is on land affected by gravity, right? Okay, so this is one more thing. Then do I have only so much? I have one more, I think. Just a minute. Let me see one more here. I think that's it. That's it. Okay. So almost around 9 to 10 different softwares we had looked into, or websites or simulators we have seen into, which deals only on the free fall. So what we have learned so far is that how to use a single concept and see to it that we can connect it to multiple branches, not multiple branches, multiple concepts of it. In fact, that will also be quite interesting to connect between multiple branches, but unfortunately for this particular concept I was not able to get, okay, so many branches. But might be I'll be looking for the other things And while we look into it, then definitely, if I get anything, I'll just put it across as much as possible. Anyway, now it is vacation going on. I'm trying to record one video, okay, which is on the same lines to describe like how experiments can be conducted, simulations can be conducted to showcase what all best we can do, okay, to teach a topic, okay, instead of just teaching only by the normal way. So what is that we can do so that we would be able to make physics more interesting. So if you really like this video, do share with everyone and your colleagues, friends, and also with students, and do practice this. It's not just sharing, but once you get to know about this, you do practice it in your classes, the schools, to see to it that, okay, how this can be done easily. With this, I think it's time, nearly half an hour I had taken. I'll stop this lecture and see you again tomorrow. Thank you. Thank you, everyone.